Okay, welcome to Math 158, Functions, Graphs, and Matrices. This is our section 6.1. We're going to talk about graphing linear inequalities. When we talk about graphing linear inequalities, we talk about graphing lines, but instead of y equals a value, it's going to be x, y is greater than or equal to, or y is less than or equal to an equation of x. Before I start, let me do a quick review here about some notation, some manipulating, and some review of inequalities as we tend to see in earlier grades in high school, maybe even middle school, depending on your background. So first of all, we've got this sign and we've got this sign. Initially, let me erase these and start over. This sign right here is less than, greater than. There's all kinds of ways that people talk about how to refer to or remember which sign is which. And I hear things about an alligator. The alligator eats the bigger number. I don't know if you guys have heard that. I think things like that are silly. Quite honestly, a little counterproductive. What I choose to do is look at what these things are as their arrows. Okay, so less than, because that would be to the left, greater than, because that would be to the right. Okay, so let's come over here and just do a little bit of review of what we might have seen before, right? So if I have x equals 4, and I'm going to graph that on a number line, 0, 1, 2, 3, 4, we put a circle at 4 to indicate that x equals 4. We have the value of x that equals 4, so we put a closed circle. If we're going to graph x is greater than 4, again, we have our 0 and we have our 4, which are really the only numbers that are essential to label here, to index on our number line. Notice that we are only wanting to have numbers greater than 4. We don't want to include the 4. If I put a closed circle on the 4, that's going to indicate that I'm including the 4, but I don't want to be including numbers. I don't want to include 4. I want only numbers bigger than 4. A mistake that many students make is they say, okay, let's start with 5 and go everything to the right of 5. Now, shading this to the right, notice, see, here's the greater than sign. The arrow pointing to the right is the greater than sign. So I want all the numbers greater than. Now, I don't want to say 5 and greater. Okay, there's an issue with that because what about 4.5? What about 4.1? What we want to do is we want to get as close to this 4 as we possibly can without including the 4. So we draw an open circle to indicate that we're as close to the 4 as we possibly can without touching. And then we want all of the numbers that are greater than 4. And again, notice that at my arrow, the end of my arrow is a greater than sign. You don't need 2 arrows. I just did that to try to stress that point. That's the greater than sign. Now, if I was going to graph x is greater than or equal to 4, here's my 0 and here's my 4. In this case, what I'm going to do is, because of the equal to part, I'm going to include the 4. And then because of the greater than part, I'm going to include all of the numbers greater than 4. Okay, so if I want to graph, let's say x is less than 7. Here's my 0, here's my 7. Am I going to include the 7, yes or no? Because there's no equal to part, I am not going to include the 7, so I have an open circle. But I want less than, so I'm going to graph all of the numbers, include all of the numbers less than 7. Okay, so quick review there on graphing. When do I have the open circle and when do we have the closed circle? The circle is open or closed depending on whether we can equal the 4 or the 7 or not equal the 4 or the 7 or whatever the number is. The less than sign or the greater than sign is what indicates the shading in one direction or another. Okay, so here, x is less than or equal to y. X is greater than or equal to y. X is less than y. X is greater than Y. You want to be comfortable with those notations. Okay. Now, if X is less than or equal to Y and you add the same value to the X and the Y, it's going to stay the same. The relationship will stay the same. X is your age, Y is my age. If X is your age and your age, X, is less than my age, Y, 2 years later, you're still younger than I am by the same amount. Okay. The same thing. If you are younger than I am, X is less than Y. You are younger than I am, and both of our ages double. You're still younger than I am. Okay. The one thing you need to catch here is number 3. I shouldn't say the one thing. One of the things you need to catch is that if A is a negative and you multiply a negative, then notice X is less than or equal to Y becomes AX is greater than or equal to AY. Multiplying by a negative negates things. And again, let's come over here to the left to talk about why that is. Here's my number line. Here's 0, 2, 4, -2, -4. We've got a series of numbers here. Okay. If we're in class, I'm going to ask you questions, wait for a response. I suppose I could ask a question now, you're not going to respond, or at least I'm not going to hear you respond, right? So if we talk about what does it mean for a number to be greater, on the number line, we are often allowed to believe, particularly at younger ages, that numbers that are greater are numbers that are farther from 0, and that's not true. That's only true if you're working exclusively with positive numbers. What it means for numbers to be greater, again, the greater sign is here. What it means for a number to be greater is that it's farther to the right. What it means for a number to be less or smaller, or let's just say less than, is farther to the left. So it's true that 4 is greater than 2 because the 4 is to the right of the 2. Now, if I negate those two and I multiply both the 4 and the 2 by a -1, I get -4 and -2. But notice now, if I look over here on the left side, which number is greater than which? Is it true still that -4 is greater than -2? Or is it the case now that since -4 is farther to the left, that -4 is actually less than -2? And it's the positional relationship of these values on the x-axis, on the number line, that indicates greater or less. So that's why if I multiply by a negative, I change the sign of the inequality. And that is something that's present in inequalities that we don't worry about in equations or in equalities, because that doesn't matter. The other thing that's true here that I want to point out in number 4 is that if x is less than y, then y is less than x. Again, if x is your age and y is my age, if your age x, if you are younger than me, well then I am older than you. Okay, so make sure we understand those in both directions. Okay, so let's look at number 1 here. In order to graph linear inequalities, you're going to start with this semblance to an equation. Okay, first of all, I have the line 3x minus 2y equals 12. Recall that to graph this line, we want 2 points. And the 2 points that you find, quite honestly, are not important. I'm going to suggest that you do similar to what I do and you find the 2 points that are easiest to find. Now, I'm hoping at this point that we don't still need to do this, but just in case, let's. If we want to make a table of values, x and y, the easiest thing to do is to put 0 in for x. If I substitute 0 in place of the x, I'll get 3 times 0 minus 2y equals 12. 3 times 0 is 0, so y will equal 12 divided by -2, which is -6. So y is -6. Don't try to decide now what other value should I substitute in for x. My suggestion would be to put in 0 for y. And if y is 0, we're going to have 3 times x minus 2 times y, which is 0. equals 12. So 2 times 0 is 0. 3x equals 12. So x will equal 4. Now we have our two values, 0, negative 6, and 4, 0. We have our two intercepts, 0, negative 6, and 4, 0. And then we have our line that goes through those 2 points. And that's the equal to. Okay, now let's suppose, hypothetically, that this sign here was not equal to, but it was greater than or equal to. Because of the equal to, we include the line. But we also want values, ordered pairs, that will make it true that 3x minus 2y is greater than 12. The way this is going to happen is you wind up including one side or the other. Either the whole region below the line or the whole region above the line. The simplest way to test this, in my perception, my understanding, my thinking, would be take the origin, the easiest value to plug in. If x and y are both 0, 3 times 0 minus 2 times 0, we're wondering, is that greater than or equal to 12? Well, 3 times 0 is 0. 2 times 0 is 0. 0 minus 0 is 0. Is that greater than or equal to 12? No. Therefore, the side where the origin is does not get shaded. The side where the origin is not does get shaded. Okay. Now, I am going to warn you, those of you who are watching this video, and you're in my course at Manchester Community College, Math 158, the textbook that the college has adopted here does things in a way I've not seen before. In this section in the textbook, they will shade the opposite side. They'll do this. They'll shade here and then write the words solution set. Okay. I've not seen that before. That's not what's normally done. More normal, get rid of that. More normal would be to just shade this side. This is what I'm looking for. If you were taking a test with me, this is what I would be looking for you to do. Okay. So let's move on to number 2. Notice that in number 2, what's different here is that we have 2x plus y is greater than 6. Now, the work we did before, graphing on the number line, I wanted to point out to you the difference between when we're equaling 4, when we're greater than 4, including the point, not including the point. Same thing applies here, just in 2 dimensions. With the equal to, that includes the line. Greater than means we're not going to actually include the line. Let's graph this the same way. Let's make a table of values, x and y. We'll put 0 in for x. So 2 times 0 plus y is greater than 6, so we would get 6. Put 0 in for y. So 2x plus 0 would equal 6, so x would be 3. Now notice here I wrote equals. I should have written equals here. If I graph this line, forget about the less than, and I just make this the line 2x plus y equals 6, I would have a y-intercept at 0, 6, 1, 2, 3, 4, 5, 6. And I would have an x-intercept at 3, 0. And then, let me try to use this ruler here, right? So then this would be our line. Except that the solid line indicates that I'm including that line. And if you look again here, we don't want 2x plus y to be equal to 6. We want it only to be greater than 6, which means that we're really not going to shade the line. Okay, let me put this back here. What we're going to do is we're not going to include the line. We just want to know where the line is. It's kind of like the open circle. And we're going to draw a dotted line. The dotted line here compares to the open circles over here. Okay? I know I'm going back and forth. I hope that makes sense. The difference between the solid line and the dotted line. Now, the other thing we need to look at here is we want 2x plus y to be greater than 6. I'm going to do the same test. I'm going to pick the origin, put 0, 0 in for x and y, 2 times 0, plus y, which is 0. Is that greater than 6? Is 0 greater than 6? No. Therefore, the origin is on the side that does not get shaded. The side that gets shaded is everything on the other side. In other words, if I pick a point over here, let's say I pick this point, 4, 4. That's the point 4, 4. 2 times 4 plus 4, that is greater than 6. 2 times 4 is 8, plus 4 is 12. 12 would be greater than 6. Any point I pick on this side will make this statement, 2x plus y is greater than 6, will make it true. Any point I pick down here below the line will make this statement, 2x plus y is greater than 6, untrue. Okay, so hopefully that makes a difference with the shading there. Okay, let's do another one. Now, number 3, I'm going to graph this one slightly different since we're given this in slope-intercept form. Nice straight lines there, right? So if x is 0, y is 2, so there's our slope. I'm sorry, there's our y-intercept. We have a slope of 3 fourths. So from here, I'm going to go up 3, 1, 2, 3, and over 4, 1, 2, 3, 4. We have those 2 points. And so now here is the line that goes to those 2 points. My question before I draw the line will be to ask you, should this line be solid or should this line be dotted? Because of the equal to part, the line will be solid. Okay. The next piece is to figure out which side do we shade. You'll notice I'll do the same thing over and over. Try the origin. That's the point 0, 0, where y is 0 and x is 0. Is 0 greater than or equal to 0 plus 2? No, it's not. Therefore, the origin is on the side that does not get shaded. It's not part of the solution set. And so we're going to shade that piece above the line. And that shading, like I'm doing there, indicates that it's all of the values that goes on forever and ever and ever in that direction as far as the line goes. Okay. Number 4, I'm going to pretend again as if we're going to graph the line y equals 2/5 x minus 3. Again, what I'm about to considering that would be kind of like if I'm going to graph x is greater than 5. 0 and 5. I need to locate the 5. 5 is right here. Then do I include the 5 or not? No, I don't. I can always put an open circle and decide, do I close it in or not? No equal to, therefore I do not. I'm only going to go greater than. So here again with this line in number 4, I'm first going to locate the line y is equal to 2/5 x minus 3. Find 2 points on that. If x is 0, y is negative 3. Slope of 2/5, we're going to go up 2 and over 5. So there's 0, negative 3. Well, I should always be labeling points. Always. 5, negative 1. I should always be labeling points. Let's go back. 0, 2, and 4, 5. You should always be labeling points. Now when I go to draw this line, I ask myself, is the line going to be solid or dotted? since it is less than only, since this is less than since this is less than only, it's not equal to, we're going to have a dotted line. And then we're going to decide whether to shade above or below the line. I pick the origin. 0 for y is less than 2/5 times 0 for x minus 3. We get 0 is less than -3. That's not true, so we don't shade the origin side. We shade the other side. Okay, that makes sense? So hopefully we're good there. Now we're going to move on. What if I have a system of inequalities? If you recall, we spent some time in a few previous videos talking about finding a solution to a system of equations. And we said that the solution to the system of equations was the point where the two lines intersect. Well, the solution to a system of linear inequalities is going to be the shaded region, where it's going to be the region where the two different shaded regions both intersect. Okay, so let's graph these two lines. Okay, so first of all, let's put some lines on here. Pretending that those are equally spaced. If I'm going to graph 2x minus 5y equals 10, first of all, if y is 0, if x is 0, y is -2, right? In 2 times x minus 5y equals 10. If x is 0, y is -2. And if y is 0, x would be 5. 1, 2, 3, 4, 5. And so here is that first line. I didn't say this out loud, but notice it's equal to, both of these are equal to, so I'm going to include the line both times. This was 0, -2, and this was the 0.50. We always want to include those points. Now, if we decide which way to shade, if I take the origin 0, 0, put 0 in for x and put 0 in for y, and is that less than or equal to 10? 0 less than or equal to 10? Yes, that is true. So I'm going to shade sparingly the side of the line toward the origin. Now when I go to graph the other line, if x is 0, 0 plus 2y equals 8, so y would be 4. 1, 2, 3, 4, so I have the point 0, 4 is my y-intercept. Then to find my x-intercept, I'm going to let y equal 0, and x would equal 8. 1, 2, 3, 4, 5, 6, 7, and there's the point 8, and that would be 8, 0. Now if I graph that line, notice again that because it is less than or equal to, solid line because of the equal to, so there's that solid line there, and now we need to decide, let me erase part of this. Now we need to decide which way to shade this one. I'll do this one in blue. Here's my origin. If x and y, let me make that cleaner. If x and y are both 0, is it true that 0 is less than or equal to 8? That's true, so I'm going to shade toward the origin. Again, if you're following the textbook instructions that are currently, the textbook that's currently being used in this course, you're going to be doing this exactly the opposite, which I think is confusing and a lot less standard, so I'm going to teach this way. But notice that there is a particular region that got shaded twice. Okay, there is this region here that did not get shaded at all. This particular region got shaded only by the first equation. This region here only got shaded by the second equation. The solution set is going to be the region that got shaded both times. So we include the line, that part of this line, we include this piece of that line, and everything in between. So that yellow region is actually the solution set for this region. Okay, and it is the picture here that's going to give you the solution set. You don't want to try to list all of those points individually. That is that shaded region. This picture is the solution set. And I realize I missed a few spots there, but we assume completeness. Okay, so number 2. It's going to be the same thing. I'm going to fix that. I suppose what I could do, right? There's my y-axis. This would give me a much better axis to work with. Okay, so now the first equation, if x is 0, y is going to be 5. 1, 2, 3, 4, 5. So 0, 5. And the first equation, if y is 0, notice x is going to be 7.5 or 15 halves. 1, 2, 3, 4, 5, 6, 7 and a half. I'm going to label that as 15 halves 0. And so here's my first line. Notice that both equations have an equal to. Therefore, both lines are going to be solid. Okay. And then now am I going to shade above or below? Picking the origin. 0, 2 times 0 plus 3 times 0, is that greater than or equal to 15? No. So I don't shade toward the origin. I'm going to shade away from the origin. I really should have arrows on the end here. The second equation, and I'll use blue for this, if x is 0, y is negative 5. 1, 2, 3, 4, 5. So that's 0, negative 5. And if y is 0, x is going to be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 0.10, 0. And so now that line is going to look like this. We really should put arrows on the end. And then if I pick my origin, am I going to shade toward my origin or away? 0 minus 2 times 0 is less than or equal to 10. Is that true? Yes, 0 is less than or equal to 10. So in this case, I'm going to shade toward my origin. My solution region is going to be that region that got shaded both times. So that's going to include this piece of this line here. It's going to include this piece of this line here. And it's going to include this entire shaded region that got shaded both times. I'm using different colors. I'm using highlighters because I have them available to me on my whiteboard. You're doing this, in pencil or whatever writing utensil you're choosing to use. If you want to use colors and highlighter, that's fine. My suggestion to you is that you just be very careful to try to make your pictures easily to understand, because it is actually the picture that is the solution region. Okay. So let's move on. Number 3 is similar, except I have an additional equation. I have 3 equations to find the solution region. Okay. Now, I think I understand in the textbook, and I keep referencing that in the current textbook we're using in Math 158 at the time that I'm making this video, by shading the part that's not the solution region stays clean. Okay, I get that logic, but again, that's not the norm. That's not how things are normally handled. So I'm going to continue to push doing this using what we see more frequently. Okay, that we shade the solution region. So here's my y-axis. Here's my x-axis. First equation. Let's use colors again. I'll use blue for the first equation, right? So if x is 0, y is -6. And if y is 0, x is going to equal 2. So here is my first equation. This got resized. Let me fix that. Okay, so there's my first equation. I plug in 0, 0. I'll get 0 minus 0 is less than 6. So we are going to shade toward the origin. Now I'm only going to put small notations. This is how things don't get too messy when I shade. Okay. Now let's use green for the next equation. Notice if x is 0, y is 6. And if y is 0, x will be 6. Okay, so here's that equation. That line. Arrows. 0 plus 0. If we have 0, if we go to a shade toward the origin or away, we put 0 in for x and 0 for y. Is 0 plus 0 greater than 6? No, so we're going to shade away from the origin. So the only part that's been shaded twice is this region in here so far. Y is less than or equal to 6. So we've got the horizontal line, y equals 6, which is going to be this piece right here. And y is less than, so origin would be 0, 0, so 0 is less than 6, so we're going to shade toward the origin. And so notice the only piece that got shaded all 3 times was along this line, along here, and inside that tiny little triangle right here. Okay, hoping this makes some sense. Number 4 may look a little, make this a little bit larger to give myself a feeling of space here. Graph the solution region of the following system of linear inequalities. And now what we want to do is we want to find the corner points. I didn't do this in number 3. We'll do it here. I want to find the 3 corner points or the corner points. So number 4, the first thing I also want to notice is these 2 additional inequalities. Okay, so we've got not only 3x plus 2y is less than or equal to 60, and x plus 4y is less than or equal to 40, and 2x plus 3y is less than or equal to 45, but x is going to be greater than or equal to 0, and y is going to be greater than or equal to 0. So let's suppose that we go here, and if we're taking notes, you might want to be careful how much space you write on here. Here's my x-axis. And here's my y-axis. But when I get to x is greater than or equal to 0, that means that I'm going to graph the y-axis, and that's everything to the right of it. Y equals 0 is the x-axis, and we're going to shade everything above it. So when we have a scenario where x and y are both always going to be greater than or equal to 0, those types of situations limit us to the first quadrant. So what I tend to do is start over and recognize, hey, notice those are both greater than or equal to 0. I'm only going to need the first quadrant. So I push my y-axis over, and I push my x-axis down, to give myself a lot more room, knowing that I'm only going to be working in the first quadrant. The other thing I'm going to suggest that you do here is, again, I'm going to use intercepts, right? If x is 0, first equation, if x is 0, y will be 30. And if y is 0, x will be 20. So that's going to give me x-intercepts of 20 and 30. Notice in the second equation, if y equals 0, x will be 40. So I probably don't want to go 1, 2, 3, 4, 5. I might be more interested in saying, let's go 5, 10, 15, 20, 25, 30, 35, 40. And kind of spacing those out a little bit more. 5, 10, 15, 20, 25, 30, 35, 40. And that's going to give us a little bit better space. Okay. Now with the first equation, if x is 0, y is 30. And if y is 0, x is 20. I really should label my x and y intercepts. I'm going to hold off at this point doing any additional labeling beyond this. Now we've already identified that x is greater than or equal to y, so that's going to be to the right of the y-axis. Y is greater than or equal to 0, so we're going to be above the x-axis. I'm going to pick my origin here. 3 times 0, 2 times 0, 0 plus 0 is less than 60. I'm going to shade toward the x-axis, or toward the origin. Second equation, let's do that in green. Notice that if x is 0, y will equal 10. And if y is 0, x will equal 40. So let's graph that guy. And again, if we take our origin, put 0 in for x and 0 in for y, we'll get 0 is less than 40. We're going to shade toward the origin again. So notice that so far everything is inside this region. Let's make this one purple. If x is 0, y will be 15. And if y is 0, x is going to be 22.5. So let's go ahead and make that 22.5 0 to get that on there. Suppose it doesn't have to be super perfect. Okay. And here's my third equation. And again, we're going to shade below. So you'll notice that our shaded region is this 5-sided region right here. Okay. And find the corner points. This region here that's shaded in red is what we call the solution region, or what we're eventually going to call the feasible region. The word feasible means possible, doable, workable, happens, it's okay. So that's my feasible region. In the problems where we're heading to, what we're going to want to do is we're going to need to identify the corner points of the feasible region. That means we need to find the coordinates of point A, the coordinates of point B, point C, point D, and point E. And I'm going to label those over here. Point A, B, C, D, and E. What are the coordinates of each of those 5 points? Now, point A is fairly easy to find in this case. That's where these two lines, x equals 0 and y equals 0, intercept. So that's 0, 0. Point B, notice the y is the y-intercept of the green line. And that was 0, 10. Point E, notice, is the x-intercept of the blue line, which was 20, 0. So we can get those fairly easily. What's going to be a little bit more difficult is point C and D. Now notice that point C right in there is the point where the green line and the purple line are intersecting. That's the point where the green line and the purple line are intersecting. In other words, what I need to do, I don't have a lot of space here, I need to find the point where the green line, x plus 4y, actually let me go over here. I need to find the point where x plus 4y equals 40. And the purple line, 2x plus 3y equals 45. 45, not 55. Right, double check. C is the point where the green and the purple line intersect. Yeah, the green and the purple line intersect. I suggest labeling these, like, right, this was line 1, this was line 2, this is line 3, so line 2 and 3 where they intersect, I'm using colors, so the green and the blue line, and so now I need to solve that system, and we've done this before, we know how to solve the system. I think what I would choose to do is multiply this top equation by 2, and the bottom equation by a negative 1, so 2x plus 8y equals 80, and negative 2x minus 3y equals negative 45. Now you could have multiplied the top equation just by negative 2, but I saw it coming that would have given me negatives. I just didn't feel like working with negatives today. 2x minus 2x is 0. 8y minus 3y is 5y. 80 minus 45 is 35, so y is 7. Now if y is 7, remember we take that 7, plug it in here, and x plus 4y equals 40, but the y is 7, so x plus 28 equals 40, so x equals 12. So that tells me that this point right here, point C, is the point 12, 7. A little bit of work here. Point D is the point where the purple and the blue line intersect. The purple and the blue line, well, the blue line is 3x plus 2y equals 60. And the purple line is still this guy here, the 2x plus 3y equals 45. Now I can do this, I can solve the system either way. The first system I chose to solve it algebraically. I could choose, if you recall, the augmented matrices, which I would not do by hand, but I could use my calculator to solve this system. And this would be a 2 by 3 matrix with the values 3, 2, 60, 2, 3, 45. All right, remember how to do this. So matrix, math, number B here, the reduced row echelon form on matrix A. And so we would get that x equals 18 and y equals 3. So this point right here, point D, is x is 18 and y equals 3. And so those are the 5 corner points of this feasible region. Couple of examples. So Cacio Pistachio Incorporated makes 2 types of pistachio nuts, dazzling red, and organic. Pistachio nuts that require food color and salt. The following table shows the amount of food color and salt required for a 1 kilogram batch of pistachios, as well as the total amount of these ingredients available each day. Okay. Use a graph to show the possible numbers of batches of each type of pistachio that Cacio can produce. Now, they can produce X batches of the red, Y batches of the organic. Now, food coloring, they're going to use 2 grams of food coloring for each batch of the red. They're also going to use 1 gram of food coloring for each organic, okay, for each package of organic. And they have a total of 20 grams available, which means the amount of grams available that they can use is going to be less than or equal to 20. You can use less than you have available, you can't use more. You can use all of what you have available, but you can't use more. Salt, same thing. 10 grams of salt for each batch of the Dazzling Red, plus 20 grams of salt for each batch of the organic, and we have no more than 220 grams of salt available. And there are our first two restrictions. We're going to call these restrictions. 2x plus 1y must be less than or equal to 20. 10x plus 20y must be less than or equal to 220. There are two additional restrictions here that you may not see immediately. X is the number of batches of Dazzling Red. The number of batches of Dazzling Red pistachio that you make has got to be greater than or equal to 0. You can make 0 batches. You can't make fewer than that. Y also must be greater than or equal to 0. So if I use the graph to show the possible numbers of batches of each type of pistachio that can be produced each day, I'm going to graph my feasible region. So let's find and I might run off my page here, my x-axis. Actually, you know what? I can push that down, can't I? Because again, I'm going to push it way down here. We know that since x and y both have to be equal to 0, greater than or equal to 0, we only need the first quadrant. Also, if y is 0, x is going to be 22. So we need our x values need to go at least to 22. But let's go 5, 10, 15, 20, 25. So 22 would be right about there. And let's go 5, 10, 15, 20 this way. Blue equation, if x is 0, y is 20. And if y is 0, x is 10. If I put 0 and 0 in for x and y, we'll notice that we're going to shade toward the origin. X is greater than or equal to 0, we're going to shade to the right of the y-axis. Y is greater than 0, we're going to shade above. So we're all in that region so far. Now we're going to graph the second equation with green. If x is 0, y will be 11. And let's just write in that 0, 11. Write 220 divided by 20. Divided by, I should be good enough at math to know for sure that that's 11. Okay, and if y is 0, x is going to be 22, which is right about here, we said, so that's 22, 0. There's the green line. And again, 0 plus 0 is less than 220, so we would shade below. So this here is our feasible region. Okay. This red shaded region is all of the combinations of different batches that pistachio can make given those restrictions. So what we're going to do now is I want to find those corner points. Let's call this point A, B, C, and D. A is the origin, so we know that that's 0, 0. B is this y-intercept, which we have identified as 0, 11. C will come back to. D is the x-intercept of the blue line, which we've identified previously as 10, 0. To find point C, what I need to do is I need to find the point where the blue and the green lines are intersecting. 2x plus 1y is equal to 20. So it's where the lines are intersecting, which is why I'm using equal to and not the unequal to. I'm just going to choose to go ahead and multiply top equation by -5 to do this algebraically slightly different. Negative 10x minus 5y equals a negative 100. 10x plus 20y equals 220. So 15y equals 120. So we're going to divide both sides by 15. And y will equal 80, right? 120 divided by 15 is actually 8, not 80. So y is equal to 8. If y is 8, what's x? Well, remember to take that 8, plug it in there. So 2x plus 8 equals 20. 2x will equal 12, and x will equal 6. So point C here is the point 6.8. And there is my feasible region. One last problem, number 6. Okay, during the first quarter of 2014, stock A cost $50 per share and was expected to yield 5% per year in dividends, and stock B cost $50 per share, was expected to yield 6% per year in dividends. You have up to $45,000 to invest in these stocks. You'd like to earn at least $2,400 in dividends over the course of a year. You're assuming the percentages aren't going to change. You're just, assuming that there will be no change. It's kind of what we have to do, right? If I want to draw the feasible region that shows how many shares in each company you can buy, I first need the question, the equation. Okay. Now we're going to buy, let's just say A shares, let's do this in black, not red. We're going to buy A shares of stock A, and we're going to buy B shares of stock B. If I spend $50 per share for stock A and $50 per share for stock B, and I can invest up to $45,000. Notice the less than or equal to, because it's up to $45,000. You're going to earn 5% interest on stock A. That's not 0.5 times A. I'm sorry, that's not 0.05 times A, because the amount of money invested in stock A is the $50 per share, and you want to earn 5% interest on that. You hope to earn 6% interest on the amount of money invested in stock B, which is $50 times the number of shares. And you want to earn at least $2,400 in interest. Also, the number of shares of stock A that you buy, as well as the number of shares of stock B that you buy, must each be at least 0. Okay? I'm going to make one more change before I go and I graph these. 50A plus 50B is less than or equal to 45,000. You know what I can do here? Well, let's just leave it. Okay. Actually, no. Can't I divide everything by 50? If I divide everything by 50, isn't that true that A plus B is less than or equal to 45,000? Divided by 50 would be 900. The other thing is 0.05 times 50. 0.05 times 50. So that's 2.5A plus 0.06 times 50. That would be 3B is greater than or equal to 2,400. And again, A is greater than or equal to 0, and B is greater than or equal to 0. Now I'm using A and B as opposed to X and Y, so when I make my axes, what is traditionally my my Y-axis and what is traditionally my x-axis, I'm going to label those differently. And quite honestly, it's not going to matter, but I'm going to put A on the x-axis and B on the b-axis. And let's just go 1, 2, 3, 4, 500, 6, 7, 8, 9, 1000, or 1000. 1, 2, 3, 4, 500. 1, 2, 3, 4, 500 more is 1000. And let's graph these. First equation, which I'm going to use blue, A plus B is 900. Therefore, if A is 0, B is 900. If B is 0, A is 900. And here's that blue line. Notice we're going to shade toward the axis, or toward the origin. A is greater than 0, B is greater than 0. So far we're inside that triangle. Now here, if A is 0, green equation here, if A is 0, B is 800. And if B is 0, A will be 2400 divided by 2.5, which is 960, which is right about here at 960. So we get that green line there. But now we want, this is greater than, you notice if we put in 0 for A and 0 for B, we get 0 plus 0 is greater than 240. That's not true. Therefore, we're shading away from the origin, and our region winds up being this tiny little sliver here. This point we said is 0, 900, and this one here we had said was 0, 800. If I want to find this point, the other point of this feasible region, I'm going to need to find the point where the blue and the green line, where those two lines intersect. So I'm going to need to know where A plus B equals 900, and 2.5A plus 3B equals 2400. I need to find where they intersect. You may or may not care for this. I'm just going to multiply both sides, or that equation, by negative 2.5. Negative 2.5A minus 2.5B is equal to, what's 900 times negative 2.5? That would be negative 2250. The second equation is 2.5A plus 3B equals 2400. Those will cancel out. Negative 2.5A plus 2.5A is 0. 3B minus 2.5B is 0.5, or half B. 2400 minus 2250 is 150. If I multiply both sides by 2, B will equal 300. Well, remember that A plus B is 900. If B is 300, A must be 600. So this corner point here, A is 600, B is 300. Okay, now I don't use the graphing method to determine, oh, this looks like it's the point 600, 300, but does that seem reasonable based on my graph that it would be? Okay, so there are my corner points. Next video, which actually is the last video of Math 158, we're going to do a couple of applications of these and what I do with that. So hopefully this makes sense, graphing systems of linear inequalities.